Mr. Thrasher back again. We are still learning about light and the physics of light. This video is about what's going on when light is being absorbed. And you might be thinking, wait a minute, Mr. Thrasher, not only have you maybe learned about absorption and reflection before in prior science classes, but we also very briefly went over it. In fact, there were activities understanding this idea of when you're seeing light, reflection versus absorption. Our focus in this video is probably something you haven't gotten into, and that is what's going on at the small scale, at the atomic level. You might know something is red because red light is reflected and all the other light is being absorbed, but what does that mean? What's physically going on when light is being absorbed? That's what we're going to get into in this video, and that's important because it's a direct segue into our next topic. Okay, here I have just another little illusion. Remember, color is kind of made up in your brain. These two circles are actually the same pixel colors, the same combination, but your brain interprets them differently based on the different alignment of these horizontal bars. So these two are actually the same color, but your brain interprets it differently. Okay, let's get into this idea of absorption. We will talk a little bit about reflection, but that won't be our focus. We know that when light hits like a green leaf, right? We talked about and we said, and you probably knew this already, the green leaf absorbs all the colors except for green. And the green light reflects and it enters your eyes. You see green, bam, that's why leaves are green. Or similarly, why the red petals look red. But again, what's going on? If we zoomed in, what does it mean for light to be absorbed? And in a little bit, what does it mean for light to be reflected? Okay, what's happening at that atomic level? To get into this, we need to, of course, revisit atoms. And atoms are a bit more complicated than how we've been approaching them. For example, here's the classic model of an atom. And you think of that nucleus, and we would say that electrons are orbiting on the outside. Now, that's an okay way to think about it, but orbits are really talking about levels of energy. And my example of this is, imagine I have a skyscraper. Imagine I have a big, tall building. And of course, you could be on the ground floor. You could be on the first floor, or the second floor, or the third floor. So instead of thinking of electrons as they're just orbiting around, these electrons have different amounts of energy. Just like people in a building, if people are the electrons, could be at different levels. And if you're at different levels, if you remember, they have different amounts of gravitational potential energy. It's not exactly the same. It's not gravitational potential energy here, but that's our analogy. Okay, the electrons can have different energies and they have different energy levels, just like people, if they're on different floors of a building, have different energy levels, different amounts of gravitational potential energy. So here's a different diagram. It looks very similar, but this is showing the orbital levels, or maybe more precisely, the energy levels of an electron. It could either be here, pretty close to the nucleus, so to speak, or it could be here. Again, you could either be on the first floor, or you could be up on the second floor. Okay, here's where atoms get a little more complicated. Okay, unlike people in a building, I can go to the first floor, the second floor, the third floor, or the fourth floor. If I had a ladder, I could climb up and be like halfway in between floors. I could be 1 inch above the floor. I could be 3.001697.4 inches above the floor, as long as I had something accurate to measure it. Now, that's our classical large-scale world. Atoms work in a different kind of way, and it is not intuitive, and it is complicated. Okay, this is getting into the science of quantum mechanics. Electrons cannot be at any level they want. They can only be in very specific levels. Here's my example. You're in this skyscraper again, and you get in the elevator. Now, classically, an elevator can go to the first floor, second floor, or third floor. But imagine you get into an elevator and you only have 4 choices. You can either go to the bottom floor, you can either stay at the ground floor, or you could be at the 35th floor, or you could be at the 40th floor, or the 43rd, or the 47th. Those are your only options. There is no in between. That's true for electrons. Unlike people, unlike us, where we can get to pretty much any gravitational potential energy we want, as long as we have a tall enough ladder, electrons are constrained. They can only be at very specific energy levels. I have another example right here. Think of stairs. You could either be here, or here, or here. But to be honest, if you have a set of stairs in your home, you probably can't stand up or go up half of a stair, right? How would you do that? Electrons have very discrete places they can be. They can only be here or here, no in between. This is what the term quantum actually means. Quantum means discrete, very specific values. 1, 7, 11, 14. Nothing in between. And in fact, if you've ever heard the term or the phrase quantum leap, it's kind of funny. Quantum leap is used a lot to refer to like really big jumps. But this is actually quantum leaps, when electrons are going to different energy levels. And they're very specific energy levels. Well, okay, what does this have to do with light being absorbed? Let's say I have an electron right here. It has a certain amount of potential energy. It's right here. Sorry, it's in a circle, but it's right here. If that electron has a certain amount of energy, remember, think of it like potential energy. If it drops down here, well, it loses potential energy. Remember, potential energy is based on height? Well, if I'm on the 3rd floor and then I drop down to the 1st floor, I've lost potential energy. Well, where does that energy go? For electrons, that energy goes into light being emitted. When electrons are jumping to different floors, they are emitting or absorbing different amounts of light. Look at this. Here's our equation. When this electron is going from here to a lower energy level, well, it's going to emit a light wave. And the frequency, the type of light wave, it's based precisely on how much energy is being dropped, how much energy you're losing going from here to here. Just like I lose a certain amount of potential energy from the 3rd floor to the 1st floor. I have this GIF, I have this diagram right here. This is a good way of looking at light being absorbed. Here I have light. Imagine this is like white light. Remember all the colors. This electron is going to absorb orange. Notice orange is gone. And if you notice, I'll kind of have to wait for this to reset. When that light is being absorbed, the electron jumps to a higher level. Let's watch again. So here are the electrons right here. It's on like the 1st floor. It's going to absorb orange light. And that energy light is enough to jump it up to the 2nd energy level. And then, did you see it drop back down? When it dropped back down, it emitted orange light again. Let's watch one more time. Okay, I'll try and talk quickly. Here we have an electron at 1 energy level. Here comes light. It's going to absorb orange. The orange goes away. It's an energy for the electron to jump up higher. Then the electron jumps back down and it re-emits that light. This is what's happening when light is being absorbed. It's going into giving those electrons energy to jump up. And how much energy you need is very specific. In this case, because energy is based on frequency, a specific energy correlates to a specific frequency. I'm going to go back to this picture right here. I'm actually going to go to a website. This diagram is again showing an atom. This is a hydrogen atom. We have 1 proton, 1 electron, simple hydrogen. But you don't see the whole circles here. This is almost like we're just seeing a sliver. But this would be the electron orbiting around and around and around. Here's 1 energy level. Here's another. Here's another. Here's another. Just like the elevator is either on the 1st floor or the 3rd floor or the 28th floor or the 50th floor. You need specific amounts of energy to get to these higher energy levels. I would love to go to the 35th floor of a building, but I need 35 floors worth of energy for me to climb that building. Okay? If I'm only given a little bit of energy, I can't make it up. With light, you need very specific amounts of light, very specific frequencies, because that gives you the specific energy. So right now, I'm firing green light. Look, let's watch. Green light. The electron doesn't absorb it. And that's because the energy of green light doesn't match the energy to go up here. I need a specific energy to get this high up. If green light gives me like this amount of energy, this is what's weird. The electron won't absorb it because the electron can only go here or here or here. There's no in-betweens. That's what I mean about this as being weird. If I increase the energy, if you look down here, I have ultraviolet, higher energy light now on the right-hand side. Let's say I slide it up to ultraviolet. Oops, slide it to ultraviolet. Even with more energy, if it's not a very specific amount of energy, the electron doesn't do anything. Look at this light wave, this photon, really high energy, high frequency, right? But it doesn't match the energy the electron needs to jump. So in order for this electron to absorb a particular color, a particular frequency, it needs to be the right amount. So I'm going to click on this button right here. This is corresponding to a very specific ultraviolet light. Oh, look at that. That matches the energy to go here. It's tough to see, but if you notice, this photon disappears, and then when the electron jumps back down, it reappears. That's light being absorbed and then re-emitted, like reflection. Now, maybe I could absorb first this type of light, and then, ooh, here's another wave. Here comes red. Or that's like a cyan. Ooh, that cyan was then enough to go from here to here. So it then gets absorbed, and then as the electron goes back down, imagine like going to lower floors of the building. Okay, it loses energy. So you absorb light. Let's try absorbing this one. It's going to absorb, ooh, look at that. It absorbs light, and then it reflects in a way, that light. See how it disappeared? But again, it's very specific. It can't be any type of light I want. Here's red. Let's fire red. Red is not enough to jump it around. But if I have just the right frequencies that matches these different energy levels, I can get that electron to jump up, to move around. Okay, so that's what's going on when light's being absorbed. It's more or less making those electrons go to higher energy levels, so the light disappears. And then when that electron jumps back down, it re-emits. It's like a conservation of energy thing. There is one other way that it could be absorbed, and that's not with electrons jumping, but it could make actually molecules or atoms rotate or sometimes vibrate a little bit. So that's sometimes possible too, but this is the main mechanism. And again, this is going to be important for our next video. What makes certain types of energy or certain types of light dangerous? Okay, but that's really the physics of what's going on for light being absorbed. Confusing, but hopefully this video helps illustrate a little bit what's happening at the atomic level. All right, thanks for watching.